Good day, students. I am delighted to have you here today. Today we'll be solving questions on 2023 October-November Physics 0625 paper 6 variant 1, which is the alternative to practical. And this is the first video among in this playlist for the physics practical. So we go straight to the question, and do not forget that this is an alternative to practical, meaning we won't be performing the practical in the laboratory setting, okay? But we'll just simulate the practical setting, and then we'll answer the question. Let's go. A student determines the weight of a meter roll using a balancing method. Figure 1.1 shows the setup. So this is the setup. Um, this is the pivot, okay, the knife edge, just any triangular object. And then this is the meter roll that you place on the pivot. So you want to balance this meter roll, yeah, so that the weight here will be balanced by the weight of the meter roll. You know, the weight of the meter roll will act at its center of gravity. Good. So the weight of the meter roll acting downwards at the center of gravity is to be balanced by the weight of this object. So the meter roll would balance horizontally. But let's look at the procedure and see what the question requires of us. The student places the meter roll on the pivot, on this pivot. She places a load P on the meter roll, on the meter roller at the 90 centimeters mark. Okay, the mass of load P is not known, but she places it at the 90 centimeters mark. She adjusts the position of the meter roller on the pivot so that the meter roller is as near as possible to being balanced. The ruler balances with the pivot at the 75 centimeters mark. Okay, so the ruler balances when this is at the 75 centimeters mark. Do not forget that if this is the 90 centimeters mark, then it simply means the calibration of the meter roll is being read such that this is 0 centimeters. Okay, this 0, not this is 0 centimeters. And here we have 100 centimeters. Yes, so that's where the meter ruler is calibrated, 0, 100. So 75 centimeters, that is where the pivot is. The pivot is at the 75 centimeters mark. Let's continue. Calculate the distance A from the 90 centimeters mark to the pivot. Distance from the 90 centimeters mark to the pivot. The pivot is at 75 and P is at 90. How do you get the distance here? Just subtract 90 minus 75. That's what you do. 90 minus 75, that should give us 15. Yeah. Record the value of A in the first row of table 1.1. This is where you start answering the question. You put your answer here. The distance is 15 centimeters. Now there's a rule to answering practical question. If every other value is in one decimal place, your answer must be in one decimal place. So you write it as 15.0, not 15. If you are getting 15, you would miss the mark. Okay? Your value must be into the same number of decimal place. Every other value to one decimal place, your 15 must be to one decimal place. If I had written 15, I would have missed the mark, 15.1. Okay, the next question. She records in table 1.1 the distance B from the pivot to the 0 centimeters end of the meter roll. What would distance be? What would it be? This is 75, this is 0. 75 minus 0 is 75. So automatically, B is 75. So these values have been written here for you. You don't have to put them there. Just read the question, understand the question, and do the rest of it. She repeats the procedure. She repeats the procedure, placing the load P at the 85 centimeters mark, 80 centimeters mark, 75 centimeters mark, and 70 centimeters mark. She records the value of A and B in table 1.1. These are the values of A, these are the values of B. You know, she repeats the procedure, placing the load P at 85 centimeters mark. So the next time she's repeating the experiment, she would shift this position of load P to this position. Okay, so when she shifts it to this position, what happened? The meter will no longer balance at this point. you have to shift the position of the balance point to a new position like this. You get it? Yeah. So let's assume this new position is, let's just say this new position is a 80, 82. Then you start calculating the value of the distance A, which is this is 85. 85 minus 82, you get the new value of A. Then 82 minus 0, you get the new value of B. So in this case, her new balance point must have been 71 centimeters mark. Yeah, it must have been 71 centimeters mark, 71.9 specifically. That must have been what she got, okay? So she will get the value of B, which is 71 minus 0, 71.9 minus 0, which will be 71.9. And she will get the value of A, which will be 85 minus 71.9. That should be 113.1. I don't know if I'm correct about that. Yeah. So, and then she would repeat the experiment again, placing the load at the 80 centimeters mark, on and on and on. So that's all. So in alternative to practical, you are not performing the actual experiment, okay? But you are just simulating what will happen. Think of what would have happened if you actually performed this experiment in the laboratory. You don't need to put this here. So let's continue. Plot a graph of A in centimeters on the y-axis against B in centimeters on the x-axis. Start the y-axis at A equals to 0, 0. Start the x-axis at a suitable value for the result. Y-axis must start from 0. Look at the values we have for the y-axis. You know what we have on the y-axis will be values of A. This will be the y-axis, and they say we should start it at 0. This will be what we have on the x-axis. Now look at the range of what you have on the y-axis from 0 to 15. Let's look at what we have on the y-axis. 0 to 15. If this is 0 to 15, if this is 2, and put this as 4, 6, 8, 10, 12, 14, 16. So yeah, so that range is going to work for the y-axis, okay? 0 to 15. The maximum value will be around 15, which will be around here, midway between 14 and 16. So our values for y-axis is settled. What about the values for x-axis? Well, x-axis ranges from 62 to 75. So we can't calibrate x-axis as 10, 20, 30, 40, 50, 60, 70, 80. If you use this calibration, then the range from 62 to 75 would only occupy this place, 62 to 75. That means at the end of the day, our graph might end up looking like this. Let me just plot what it's likely to look like. Our graph might end up looking like this. So we'll have the full span for the y-axis. As for the x-axis, if you just vary within this short range, okay, as seen on this slope, the x-axis is varying within a short range. So we can't use that range for the x-axis, okay? You can't use this range for the x-axis. You can't start the x-axis from the origin because of the range of value. The range is very, the range is, let me calculate the range, 75 minus 62.5. 75 minus 62.5, that should be 5 minus 2 is 3. That will be 12.5. So the range of value we have on the x-axis is 12.5. Okay, and consider that 12.5 to this range of up to 80. 10, 20, 30, 40, 50, 60, 70, 80. 12.5 out of 80. So you see that it's not covering the entire range. Unlike the y-axis, where the range is covering most of what we have on the y-axis. What's the range on the y-axis? 15 minus 7.5. That will be 7.5. So the range for the y-axis is like half of the entire values Okay, 7.5 is half of 15. But here, the range here, out of 80, the range here is 12.5, which is less than 20% of the entire span. Yeah, 12.5 over 80. That should be less than 20%. So you can't actually start the x-axis from the origin. Okay, yeah. Considering the values we have, we can start the x-axis from 60. We can let it go from 60 to 80. 60, 65, 70, 75, 80. Yes, you can let it go from 60 to 80. 60. If this is 60, or we even start from 62, 64, 66, 68, 70, 72, 74, 76, 78, 75, from 62.5 to 75. Okay, from 62, 63, 62.5 will be here, 75 will be here. Okay, that's a good range. Yeah, so this will be the range of values on the x-axis and y-axis. Okay, this will be the range of values. So if you are plotting a graph, um, because we are plotting a graph, the most important thing on a graph, you must have your axis. Okay, so we have to draw our x-axis and our y-axis. Let me start by drawing my y-axis. You use straight ruler, please. The reason why I'm not having a perfectly straight line is because I'm not using my ruler, since I'm doing this on my laptop. Make sure you use a straight ruler and very sharp pencil to draw this line. So your line must be perfectly straight. Okay? Yeah. So that's set. So let me erase this. I need to write here. So what have we plotted on what value have we plotted on the y-axis? So on the y-axis, what we are plotting on the y-axis are the values of A. So I'm putting A in centimeter here. I'll just put A in centimeter. And then on the x-axis, I'll put B in centimeter. Yes. Okay. Now let's start slotting in the values. When A was 7.5, B was 62.5. When A was 7.5, when A is 7.5, 6, 6.2, 6.4, 6.6, 6.8, 7, 7.2, 7.4, this 7.5, this 7.5. So we will trace this to this middle is 7.5. We trace this to 62.5 along the b-axis. So let's look for 62.5 along the b-axis. This is 60, this is 63, sorry, this is 62, this is 63. 62.5 will be, let me adjust this. This is 60, this is 62, this is 64. Between 62 and 64, there are 10 divisions, so each of them will be 0.2 units. 62.2, 62.4, 62.6. In between will be 62.5. So this will be 62.5. I'll use dotted line to trace 62.5 upwards. This is where they meet. So I'm putting the cross here. Good. That's it. All of these are not needed, so I can remove them. All right. The next values, when A is 9.4, B is 65.6. 9.4 goes with 65.6. 9.4, 9.4, 8, 9, 9.2, 9.4. 9.4 goes with 65.6. Let's look for 65.6. Let me just confirm it. 9.4 goes with 65.6. 62, 64, 66, 62, 64.2, 64.4, 64.6, 64.8, 65, 65.2, 65.4, 65.6. This is 65.6. So I'll trace it upwards, following this line upwards. I think this is where it will get to. Yes, so where they meet, I'll put a mark here, a cross. Yeah, a plus sign. The next values are 11.3 and 68.8. 11.3 and 68.8. 11, 11.3, 10, 11, 11.2, 11.4. Between 11.2 and 11.4, we have 11.3. So I use dotted line to trace it. 11.3 goes with 68.8. 68, 68.2, 68.4, 68.6, 68.8. This 68.8. So I'll trace this upwards. So when you're doing this in the laboratory, when you are doing this on your answer sheet, you make sure you use dotted lines. Please, all of these I'm doing, don't just watch this as if it's a movie. Download this question paper and you practice with it. Okay, while you watch this video, all of these I'm doing, make sure you are doing this on the question paper. I will put a link to this question paper on the description of this video so that you can download this question paper and do exactly what I'm doing. That's the only way you can know it and you'll be able to replicate this during your exam. If you don't practice this exact question paper and do exactly what I'm doing, you might not actually learn it. You might even be sleeping while watching this video. The video will be boring to you. But if you are practicing this, if you are doing exactly what I'm doing, then you won't sleep off while watching this video. The next one will be 13.1 and 71.9. 13.1, 12, 13, this is 13.2. Between 13 and 13.2, we have 13.1. So 13.1 will be this middle point. This is 13.1. So I place my dotted line from 13.1 and I'll take so it is very important you use your ruler. With your ruler it's a bit faster. Okay, 13.1 goes with 13.1 goes to 71.9. 71.9. This is 68, 70, 71.9. That's what I'm looking for. 71, 71.2, 71.4, 71.6, 71.8. 71.9 will be this middle. This is 71.9. So that's what I'm tracing upwards, 71.9. Okay, and then we plot the last values. 15.0 and 75.0. Okay, this should be easy. This is 15. No, it should be the middle line. This is 15. Fifteen goes with 71. Let me confirm that, please. 75.0, 75. This is 74. This is 76. Between 74 and 76, we have 75.0. And this is the point we're looking for. All right, now that we have done all of this, we are going to draw the trend line, okay, a regression line through all of these points. And we are going to draw a straight line through all of these points. Did I get this correctly? How many points do I have on the left? 2 points on the left, 1 point on the right, 2 points on the line. Well, this is okay. This is still okay. Let me see if I can get a better line. Let me use a different color. See if I can get a better line. This is not a better line. So actually, you must use your ruler when doing this. Otherwise, you make so many mistakes. Is the black line straight? Okay, let me erase the blue line. I think I like the black line. So these two points fall on the line, and the points on the left are 1, 2, 3. No, that's not good enough. This is not good enough. It's very important. If you use your ruler, only one line and you get it correctly. Okay, it's because I'm using freehand sketching. That's why I'm making so many attempts. If you use your ruler, just one straight line and you will get it correctly. Okay, yeah, so that's how you do it in the laboratory. Let me see what I have. I have 1 point on the left, 1 point on the right, then I have 1, 2, 3 falling in. Okay, this is still okay. Yeah, so this is a good regression line. Yeah, so that's it. That's how you answer questions on this topic. Let's see. Determine the gradient G of the graph. Show clearly on the graph how you obtain the necessary information. So to obtain the gradient is the y dx, okay, change in y divided by change in x. That's how you calculate gradient. Is my line good enough to be able to get a gradient? Well, it's fine. I can get a gradient from here. So to get gradient now, you have to draw a big right angle triangle. So let me draw my big right angle triangle here. I'm using color black. I hope color black is obvious. Anyway, I just want to use color red so that you can easily see it clearly. But ideally, you don't have to use different color when doing this, when doing your practical, okay? But I'm just using red so as to be clearly seen. You draw a big right angle triangle, and you pick your value from the right angle triangle. You just pick, consider 2 points that can be clearly seen. Just draw a big right angle triangle. Yeah, so the value you have here, the value you have here, those are the values of x1, comma, y1. And the value you have up here, this will be the values of x2, comma, y2. What's the value of x1? What's the value of x? What value do you have here? Let's look for the value you have here. Okay, if you trace this point downwards, you want to see the value we have down here. So let's trace it downwards. From here, I'm tracing it downwards. What value do you have here? This should be 62.8. This is 62.2, 62.4, 62.6, 62.8. This is 62.8. That's the value of x1. Okay, this is 62.8. So gradient G equals to dy dx. That's y2 minus y1 divided by x2 minus x1. The value of x1 is 62.8, so we already have that as 62.8. That's the value of our x1. Let's get the value of x2. The value of x2 is what we have here. We trace it downwards. Okay, we trace this one downwards. Let me trace it downwards. Yeah. So you trace it downwards. What value do you have here? Let's see. This is 76, 76.2, 76.4. That's 76.4. 76.4. Yeah, so I started by putting the value of x1 here. This minus, I put it here. X2, I put it there. Then let's go. Y2 minus y1. What is y2? Y2 is the value you have. Take note that I call this one x2, y2. To get x2, I trace it downwards. To get y2, I will trace it to the left, to the y-axis. What value do we have here? If this is 14, 14.2, 14.4, 14.6, 14.8, this is 15, 15.2, 15.4, 15.6, 15.8. 15.8, that's the value you have there. 15.8 minus y1. I call this point x1, y1. To get x1, I trace it downwards. I got the value of x1. To get y1, I will trace it to the left towards the y-axis, and that is 8. That is 8. 8.0. Take note that I call this point x1, y1. So in order to get x1, I trace this point, I trace it downwards to get the value I have on the x-axis. This is the x-axis. So to get x1, I trace it to the x-axis. To get y1, I trace this point to the y-axis. This line here is called the y-axis. Also, I call this point x2, y2. To get x2, I will trace this point here downwards to the x-axis. And the value I have here is what I have, is what I recorded, okay, as x2. And to get x1, sorry, yeah, as my x2. And to get y2, what I have here, this point here, I'll trace it to the left, to the y-axis. And that's how I got my y2. So this mark is not necessary. I can remove it. This one here, I don't need it. I only use it to emphasize on that point. Let's go. 15.8 minus 8. 15 minus 8 is 7. So 15.8 minus 8, that will give me 7.8 divided by 76.4 minus 62.8. 76.4 minus 62.8. No, this is 6.8. Let me confirm that. 76.4 minus 62.8. 76.4 minus 62.8. I got 13.6. 13.6. 7.8 divided by 13.6. 0.57. So 0.57 is my slope. 0.57. Easy. Let's see. Show clearly on the graph how you obtain the necessary information. This is how I obtain my necessary information. I do the slope, okay, and then I trace this line to the left to get my y2. I trace it to the left to get my y1. I trace it downwards. I trace it downwards to get my x1, and I trace it downwards to get my x2. So that is how I got the necessary information I use to plot the graph. Let's finish it up. Okay, the next part of the question says, the weight W of the meter roller is numerically equal to 2G. Calculate the weight W of the meter roller. Weight is equal to 2G, so you just do 2 times 0.57. That should give us probably 11.4. No, 1.14. Let me just confirm that. 0.57 multiplied by 2. So with the calculator, I got 1.14. So it shows that my calculation is correct, 1.14. And yeah, calculate the weight. Weight is measured in Newton. This is physics. The answer must always go with the SI unit. And please, I prefer to write with color blue. Okay. Yeah, I just use color red because I wanted it to be obvious that I'm drawing a big triangle here. You must draw a big rectangle triangle. Please make sure you use your ruler throughout this experiment. It's very important. Then x2, y2 is not necessary. X1, y1 here is not necessary. I just use it to emphasize on the fact that the first values are my x1 and y1, while the one at the top are my x1 and y2. I mean, the values here are my x1 and y1, and the values here are my x2 and y2. That's all. Okay, we go to the next part of the question. So just one practical reason why it is difficult to obtain accurate readings of A and B. Why would it be difficult to obtain accurate readings of A and B? Where is A? A is the distance between the balance point here and the pivot. So why would it be difficult to obtain the accurate reading of A and B? Well, when you attach this load to the meter rule, what happens? Will be able to see exactly where the center of this load lies on the meter rule? No. So it's very difficult to get the center of the load. Okay, yeah. So, and the distance A is from the center of the load to the pivot. So it's difficult to get the exact center of the load. The another thing is that the load might be slipping, though you can counter that by using paper tape to tape the load at the point. But the most difficult one is to find the exact position of the center of the load. Okay, so just one practical reason why it is difficult. Um, it is difficult to locate the exact center of the load. Yeah, so that's the main difficulty you can encounter. Using only one apparatus provided for the experiment. Using only the apparatus provided for the experiment, explain briefly how you will determine the position of the center of mass of the meter rule. For the definition of center of mass is the point where the entire load is concentrated. So how do you find the center of mass? All you have to do is the meter rule, place it on the knife edge and wait, allow it to balance. Adjust the position of the meter rule on the knife edge till it's balanced. Once it's balanced, then you've found the position of the meter rule. You found the position of the center of gravity on the meter rule. That's all. Place the meter rule on the knife edge is called pivot and balance it. The point where it balances is its center of gravity. That's all. Easy. Of course, it is easy. Yeah, so that is the end of question number 1. We go straight to question number 2. A student investigates the resistance of a resistance wire. Figure 2.1 shows the circuit that he uses. The student places a sliding contact C. Then this is a sliding contact C at a distance L equals to 20 centimeters from B. Distance here is 20 centimeters. He measures the potential difference PD in voltage across length L of the resistance wire. He measures the current I in the circuit. So he measures the potential difference, the voltage here, and then he measures the current flowing in the circuit. The 2 meters are shown in figure 2.2. Write down the current I shown on the student's ammeter. Where is ammeter? This is an ammeter. So if this is 0, you count 10, you get to 0.2. You count another 10, you get to 0.4. That means each of these is 0.02. Okay, 4.02, 4.04, 4.06, 4.08, 0.5, 0.5 to 0.54, 0.56, 0.58, 0.6, 0.6 to 0.64, 0.66, 0.68, 0.7, 0.7 to 0.74, 0.76, 0.76. Let's see what we have on the voltmeter. 0.76 amperes. On the voltmeter, this is 0, this is 1. That means each of them will be 0.1, 0.1, 0.2, 0.3, 0.4, 0.5, 0.5 volts. Yeah, that's it, easy. So 0.76 amperes, 0.76 amperes. Record the potential difference V shown on the student's voltmeter on the first row of table 2.1. Potential difference is 0.5 volts. You don't have to write the unit, just put 0.5. Yeah, okay, easy. Calculate and record in table 2.1 the resistance R of 20.0 centimeters of the resistance wire. Use the equation R equals to V over I. So to get the resistance, we divide the voltage by the current. R equals to V over I. The voltage here is 0.5 and the current is 0.76. So 0.5 divided by 0.76. Yeah, R equals to V over I. Um, Voltage is 0.5, the current is 0.76. So I just do 0.5 divided by 0.76. 0.5 divided by 0.76. 0.66. 0.66. 0.7 when written to one decimal place, 0.7. Yeah. So your values must be in trend. Your values must be to the same number of decimal place. Is very important. Everything must be to the same number of decimal place. Let's see the next part of the question. Calculate and record in the first row of table 2.1 R over L for L equals 20 centimeters. So the resistance is 0.7. So you divide 0.7 by 20. That will be 0.035. I hope I'm correct. 0.035. Okay, that's it. What's next? Write a conclusion about the relationship between R and L. What's the relationship between R and L? I don't need this here, so I can easily remove it. Relationship between R and L. Look at R and look at L. Sorry, no, this is R, this is L. As L is increasing, R is also increasing. That means R is directly proportional to L. That's it. Yes, as R is increasing, the length L is increasing. What would the relationship be? Okay, so now you can see that write a conclusion about the relationship between R and L. R is directly proportional to L. Yes, the resistance is directly proportional to the length. Okay, yeah, and if you were to find a multiplication factor, just do 20 divided by 0.3. 20 divided by 0.3, you get 66.666. So 20 divided by 0.7, that was a mistake. 20 divided by 0.7, 28.57. Yeah, or we can say um, R equals to L divided by 28.57. And let me just approximate, put this to two significant figures. R equals to L over 30. So two significant figures. Yeah, 29. Two significant figures. L over 29. Yeah. So that can be considered the relationship between R and L. For instance, where L is 20, divide 20 by 29. You should get the value of R. When L is 60, divide 60 by 29. You should get the value of R. When L is 100, divide 100 by 29. You should get the value of R. Yeah, so that's how I got this relationship. Okay. Yeah, so you just say R is directly proportional to L. As R increases, L increases. Okay. Yeah, I think that's good enough. We go straight to the next part of the question. Okay, sorry, before going to the next part of the question, I said R equals to L over 29. Okay, that's actually the mathematical relationship. Okay, if you want to calculate the mathematical model of the relationship between R and L, R equals to L over 29. Or you put it in simple term, R over L equals to, you can just find the average of these values. 0.35 plus 0.35 plus 0.33. Divide all of this by 3. Okay, your answer will be around 0.3, 0.34, yeah, 0.34. Let me just do that. 0.035, 0.035 plus 0.035 plus 0.035 equal to, divide everything by 3, 0.035. Whoa, no. 0.035 plus 0.035 plus 0.033. That was the mistake I made. You get this? Divide everything by 3. I'm finding the average. I got 0.034. So you can just say R over L equal to 0.034, okay? Or you say R over L equals to 0.034. Okay, I've picked an average value. Yeah, so that's the relationship. Okay, yeah, or you say R equals to 0.034 L, which is normal. Okay, yeah. If you want to get R, for instance, you want to get this R, multiply this L by 0.034. 20 multiplied by 0.034, you get the value of R. 20 multiplied by 0.034, you get 0.68, approximately 0.7 to 1 decimal place. So that's it. That's how scientists work in the laboratory and arrive at different conclusions. Justify your conclusion by reference to the results. Okay, justify your conclusion by reference to the result. Let's look at the results we have. Okay, from our results, in fact, the justification we have already done. The justification we have already done, that was what we were doing at this time, okay? Because what justification do you have? Because R is directly proportional. Okay, this is where I was supposed to do this justification. Proportional to L. How? How did he get that? How did he get that? We got that by looking at the trend of values. As R is increasing, as L is increasing, R is increasing, and we saw that if we pick, if you consider R over L, we take the average, we get R over L equals to 0.034. Okay, yeah. So it is from these values that we got that R over L equals 0.034. As hence, hence R over L equals to 0.034 and R equals to 0.034 L. Yeah, R is directly proportional, so that's the justification. Write a conclusion about the relationship. This is our conclusion about the relationship, and the justification is that R is directly proportional to L. This is not where we write the conclusion, okay? This is not where we write the justification rather. Our conclusion is that R over L equals 0.034, or you say R equals to 0.034 L. That's our conclusion. How did he arrive at this conclusion? This is how we arrive at the conclusion. Okay, we consider the fact that R is proportional to L, hence R over L equals to 0.034 from the data. Yeah, or you just simply tell them that R over L equals to 0.035 plus 0.035 plus 0.033 all divided by 3. Please, you write this on a single line. Don't write it like this. It's because of space that I've written it like this. So you show how you got the value, and then you say R over L equals 0.034. So that's the justification that made you arrive at that conclusion. R over L equals 0.034. Hence, R equals to 0.034 L. Use the values in table 2.1 to estimate the resistance R2 of 2.0 meters of resistance wire. Show your working. You know, R equals to 0.034 L, where L is the length in meters. Convert your length to meters. L equals to 2.000 meters. Convert to centimeter. You know, because your L in the table is given in centimeters. Take note that from the diagram, the distance is given in centimeters. Yeah, L in centimeters. In fact, and you're supposed to put this here so that you don't get confused. Yeah, centimeters here, voltage in volts, R in ohms, and R over L in ohm per meter. So it's very important you put those values on the at the heading. Yeah, at the heading of the table, so you don't make mistake. And yeah, so now we've converted our L to meter by multiplying by 100. That should give us 200 centimeter. We've converted our L from meter to centimeter by multiplying by 100. Now we do our R equals 0.034 L, 0.034 multiplied by L, our L is 200. 0.034 multiplied by 200, let's see, 1, 2, that will be 3.4 multiplied by 2. 3.4 multiplied by 2 will give you 6.8 rather, 6.8 ohms. That's the end of that question. We go straight to question number 3. So we go straight to question number 3. A student investigates the magnification of the image produced by a lens. Figure 3.1 shows the setup. So we have an illuminated object. The distance between the object and the lens is u, and the distance between the lens and the screen is v. The screen will be captured on the image will be captured on the screen. So v represents the distance between the image and the lens, while u represents the distance between the object and the lens. On figure 3.2, measure the height h subscript 0 of the illuminated object. So what you do is you place your meter rule here and you measure this height here. So when I place my meter rule here, I got 15 centimeters. So I'll write that here, 15 centimeters as the height h subscript 0, 15 centimeters. The next one, figure 3.1 is drawn to 1/10 scale. On figure 3.1, figure 3.1, yeah, okay, figure 3.1 is drawn to 1/10 scale. On figure 3.1, measure the distance u. So you measure this distance, and if you place your meter rule here, you get, let me see. Yeah, when I place my meter rule here, I got 2 centimeters. 2 centimeters. You get it? 2 centimeters, that's u. So you write 2 centimeters. This is, no. This is 1.5 centimeters, please. 1.5 centimeters. If you place your meter rule here, you get 1.5 centimeters. Yeah, you place your meter rule here, you get 2 centimeters. So figure 3.1 Okay, measure the distance u. Okay, that we have done. The actual object distance u is 20 centimeters. Yes, of course, because it is drawn to 1/10 of scale. So whatever distance you get, just multiply by 10. So this 2 centimeters, if you multiply by 10, you get 20 centimeters. Okay, so it makes sense when it is said that the actual object distance u is 20 centimeters. The student places the lens at distance u equals 20 centimeters from the illuminated object. So yeah, so the real practical now, okay, the diagram, we have 2 centimeters, but the actual experiment, okay, so because this diagram is shrunk, okay, it's diminished by 10 times, okay. So the actual distance will be 20 centimeters. And okay, let's continue. He moves the screen slowly until a clearly focused image is formed on the screen. So after placing the object at a distance of 20 centimeters from the lens, then this screen, it starts moving it closer to the lens. If it's not working by moving it closer, then you'll be moving it far away from the lens until a particular point when the image on the screen is sharp, then you stop and then you measure the distance v, distance between the lens and the screen. Okay, he measured the distance v between the center of the lens and the screen. On figure 3.1, the distance is represented to scale by distance v. Use figure 3.1 to determine the actual distance v between the center of the lens and the screen. Show your working. So you place your meter rule here, you measure this distance. So I want to place my meter rule here to measure this distance. So with my meter rule, I got 8 centimeters. Yeah, so this distance is 2 centimeters, this distance is 8 centimeters. And you know, this diagram is 1/10 to scale. So if you want to get the actual reading, this distance, just multiply it by 10. You get 80 centimeters. That's the actual distance. The question requests for the actual distance, okay? Determine the actual distance. So the actual distance is 80 centimeters. Let's continue. Calculate and record in table 3.1 the magnification m using the equation image distance divided by object distance. That gives you the magnification of a lens. The student measures the height of the image h1 that is formed on the screen. The reading is shown in figure 3.1. Before that, let's start by calculating the magnification. Magnification is v over u. The actual u is 20, actual v is 80. So magnification m is v over u, which is 80 divided by 20, which will give you 4. That's the magnification of the lens. Magnification of the lens is 4. Calculate and record in table 3.1. Yeah, so where's magnification? Magnification. The magnification m, yeah, so m is 4 for the lens, okay? Okay, let's continue. The student measures the height of the image h1 that is formed on the screen. The reading is shown in table 3.1. So the height h1 is 5.9 centimeters. The student measures the height h1 of the image that is formed on the screen. The reading is shown in figure 13.1 in table 13.1. So this height h1 is 5.9 centimeters. That's fine. Calculate and record in table 3.1 the ratio h1 over h0. H1 is H1 is 5.9 centimeters. H naught, H subscript 0. Do you have H subscript 0? Where is H subscript 0? H subscript 0, that's the reading you have here, which is 1.5 centimeters. So if H1 is 5.9, then H1 divided by H subscript 0 will be 5.9 divided by, our H subscript 0 is 1.5. So you do 5.9 divided by 1.5. Use our calculator to do that. Let's use our calculator. So 5.9 divided by 1.5 gave me 3.93. 3.93, that'll be 3.9, because the value here, everything is written to two decimal place. Oh, sorry. This magnification here is 1.16. So the magnification I'm writing here should be 4.00. Okay, to two singular figure. So to two decimal place rather. The student repeats the procedure using u equal to 30 centimeter. V, the V I got here is 80. Have I recorded it? Use figure 3.1 to determine the actual distance V between the center of the lens and image. Okay, I've done that. I've recorded the V. What else? I want to see if I'm missing anything. This is V. Okay, when U is 20, V is 80. Okay, 80.0. Yeah. When U was 20, when U was 20, V was 80. So I recorded that as 80.0 centimeters. Yes, okay, so everything is fine. The student repeats the procedure using u equals to 30. So the second experiment, he changed u to 30 centimeters. The readings and the results are shown in table 3.1. So when u is 30 centimeters, v became 34 centimeters. Multiplication was, if you do v over u, you get 1.16. H1, H1 is what? Height of the image, okay? H sub 0, height of the object, 1.2, fine. After the students, another student suggests that the multiplication m is equal to the ratio h1 over h0. States whether the results agree with the suggestion. Justify your statement by reference to the results. Let's see if the multiplication is h1 divided by h0. h1 is 1.8 and h0, oh, of course, height of objects is the same object that we use. So the height of the object remains 1.5 that we had initially. So height of object is 1.5, height of image is 1.2. So height of image is 1.8 rather. So if you do height of image 1.8 divided by height of object is 1.5, let's do it. 1.8 divided by 1.5, 1.2. Yeah. So they said the student, okay, another student suggests that the magnification m is equal to the ratio h1 over h0. When we did h1 over h0, we got 1.2, okay? Yeah. And what was the magnification we got? Our magnification was 1.16, which is approximately equal to 1.2 if you are writing to two significant figures. If you want to write this to two significant figures, we have 1.2 to two significant figures. So it's fine. Statement states whether your results agree with the suggestion. Yes, my results agree with the suggestion. Justification. When the magnification is written to two significant figures, we got 1.2, which is equal to the ratio of of h0 to, sorry, h1, h I'm image to h0, h object, h image, okay, I write hi H object, yeah. So when you go the magnification to 2 figure figure, we got the same thing. So that justifies our answer. When you do multiplication is 1.16, and if you take the ratio of this, if you take the ratio of image height to object height, object is the illuminated object. The size of the object or the width of the object does not change. We use the same object, and remember we got 1.5 for the object. Yes, so 1.5, which would go for the object. The image in this case, the image is 1.8 divided by the object, which is 1.5. We got 1.2. Okay, so fine, they did an accurate job, fine. But if you compare our magnification here with the value we have here, then our answers are correct. Okay, if you even compare h image, height of image divided by height of object, if you compare it to the magnification here, they are close. Okay, yeah, they are close. Yeah, you can even proceed further by saying the value the value of m, all the values of m are close enough to the values of height of image divided by height of objects. So the value of the magnification is close enough to the ratio of height of image over height of objects. So that's it. You get your full 2 marks for that answer. So just how you would continue to use the same apparatus to test the suggestion that the magnification m is equal to the ratio height of image over height of objects. How will you continue to use the same apparatus? This is the apparatus, and the student started with image distance 20, right? Yeah, he started with image distance u 20 and adjusted he started with object. This is the object. Distance between object and the lens was 20 initially. So he started with object distance 20 and they adjusted the screen, thereby adjusting the image distance. The second case, during the second experiment, he used the object distance of 30 and then adjusted the screen. So he was adjusting the image distance. The third case, he can use the object distance of 40, okay, and then adjust the screen to adjust the image distance. So that's what you can do. Okay, the first case, object distance was 20. Second case, object distance was 30. So you continue to increase the object distance to 40, 50, 60. So just how you would continue to use the same apparatus to test the suggestion that magnification m is equal to the ratio. So what would you do? I'll use other values of m, or I will repeat this. Yeah, I would repeat the experiment using other values of the image distance, such as, so I'll use 40, 50, and 60. Okay, then the I'll record my readings. What are the readings that I'll take? I will take image distance, image height. I already have, of course, okay, fine. All the values of u, 30, 40, 50, I'll also record it on the table. U, that is object distance, and the height of the object does not change. Record my readings. We record all of these on the table and compare, or you just say compute, or you say calculate m and um, height of image divided by height of object. Then you compare them, compare m and height of image divided by height of object. You may even proceed to plot a graph. Okay, yeah, when you plot a graph, then you notice that let me see. Let me look at the values we have again. Yeah, so you may proceed to plot a graph, and when you plot a graph, if you get a straight line graph, that's it. That's good enough. Oh, yeah, that's all. We are through with question number 3. Now, question number 4, planning. This one, you don't have the procedure. You will plan the experiment yourself. A student investigates the time taken for water to evaporate to dryness when heated from above. Figure 4.1 shows the setup. The power of the heater is constant. The following is also available. We have a supply of water at room temperature. So we have water at room temperature here. Meter rule. So you have a meter rule to take reading of length or height or distance. Plan an experiment. This is planning. Plan an experiment to investigate how one factor affects the time taken for the water to evaporate. So the time taken is the dependent variable here. Okay, the time taken to evaporate depends on certain factors. What are those factors that can determine the time taken for water to evaporate? Okay, so let's see. You do not need to write about safety precautions. You should state any additional apparatus required. Explain briefly how you would do the investigation. State the key variables that you would keep constant. Draw a table or tables with column headings to show how you would display your headings. You are not required to enter any readings in the table. Explain how you would use your readings to reach a conclusion. So that's all. Now, if you are solving question number 4, okay, question number 4 involves planning. Okay, all IGCSE paper 6 question number 4 is on planning. And now, if you want to plan an experiment, all you have to do is just provide answers to this checklist. All of this checklist. Provide answers to this checklist, and that's all. Once you're able to provide answers to all this checklist, you get the complete answer to the question. Okay, you get the correct answer. But by the way, before doing that, let us start to understand the question. There is an infrared heater, infrared rays. Rays of infrared, that's infrared rays, they carry heat, okay? So it involves heating. The rays would shine on this tray, okay? So infrared rays will be incident on this shallow dish of water. And you want to check how certain factors affect the time taken for the water to evaporate, for all the water to evaporate. Okay, plan an experiment to investigate how one factor affect the time taken for water to evaporate. How do you calculate the time taken for water to evaporate? Now let's see, what are those things that can affect how long it takes for water to evaporate? Number one is what? Um, Number one is first of all, how do you measure the rate at which the water is evaporating? You can place the meter rule here and observe how the level of water, this is the level of water, this height, okay? The height will be reduced to this level, okay, and continue to reduce till it reaches the ground level, okay? Yeah, so you are using the meter rule to measure the depth of water, okay, to measure the height of the water. So the height of water will be reducing. What is the factor that would affect the rate at which the height of water reduces? Number one, we can talk about You can talk about wind. If you have wind blowing over the water would evaporate. Of course, evaporation will be faster when you have wind. Another thing you can talk about, you can consider is the surface area that is exposed. Okay, so if you use something to cover this region of this tray, evaporation will not be able to take place here. Evaporation can only take place within this part that is open. Okay, so you can reduce the size of this cover, remove the first one, put a smaller cover. Okay, then you notice the evaporation will be slower. After some time, you remove this bigger one again and replace it with a smaller cover. You notice that evaporation will be slower. Evaporation will be faster as the size of the cover is reducing. Okay, so another thing you can consider is temperature. Okay, consider the brightness or the intensity of infrared rays that are coming. When the intensity of infrared rays that are coming is much, evaporation will be faster. Okay, but when the intensity is not high, evaporation will be slower. Now it is time for you to plan. Okay, put it into writing how you want to carry out this experiment, how you want to carry out this investigation. Okay, so putting it into writing, let me remove this, all of this. Number one, state any additional apparatus required. What exactly do you want to do here? You know, we are not, we are just told to plan an experiment to investigate how one factor only affect the time taken for water to evaporate. So you just want to consider the time taken for all this water to evaporate, okay? Yes. What are the apparatus we have? We have supply of water, we have meter rod. But you have to focus on the time taken, okay? So state any additional apparatus required. Timer, because you have to check the time taken. Number one, timer, in order to check the time taken. Now, which factor do you want to use? Explain briefly how you would do the investigation. Now, this is when you have to plan how you want to carry out this investigation. What factor do you want to use to determine the time taken? Okay, to see how it affects the time taken for all this water to evaporate. You know, I've talked about intensity of light, but you were not told that this infrared heater, you can adjust the intensity. So you can't go there because you were not told that you can adjust the intensity. What else do we talk about? I talk about using a cardboard to cover the surface of the water. Fine, that's also going to work. Which other factor can you adjust? Okay, blowing wind over the water, yes, that can also work. But we want to pick something that you can easily carry it out in the laboratory. Something that when you adjust this, you can easily see it. Don't rely on your knowledge of theory. I was talking about the other time, we were trying to bring the theoretical knowledge into it. But don't rely, when it comes to practical planning, don't rely on your theoretical knowledge. Try to see the question as if you had no prior knowledge of the topic. What can affect the rate of evaporation here? You know very well that when water is plenty, it takes when the volume of water is much, it takes a long period of time for water to evaporate. When the volume of water is small, it takes a very short period of time for water to evaporate. So what you can consider is the volume of water. Yes. So when you fill the water to the brim, consider how long it takes the water to evaporate, okay? Then later, don't fill it to the brim, fill it to a certain level, and measure the time taken for it to evaporate. After that, reduce the volume, measure the time taken, then reduce the volume to a very small amount of water, measure the time taken. So you can check how volume of water affects the time taken for water to evaporate. Another thing you can also consider is the distance between the heater and the water. You know, I talked about intensity of light, but you cannot, there is not, there is no explanation of you increasing the current flowing through the heater or reducing the current flowing or reducing the current, okay? How will you increase or reduce the current flowing? So I don't want to bring that into it because it will make it complex. What you can easily adjust that will vary the intensity is the distance between the heater and the water. So if the distance is high, then the intensity of infrared reaching the water will be low. If the distance is small, okay, then almost all the infrared rays that are coming from the heater, almost all of them would get to the heater. Okay, that means the intensity of heating will be much. Okay, so you pick which one you want to write on, and once you pick, follow it. If you want to pick distance between the heater and the tray of water, follow it. And if you want to pick the volume of water in the tray, follow it. Okay, yeah. So we have a meter rule, right? So what we use meter rule to measure? We use meter rule to measure the depth of water, the volume of water. Okay, that's if you are using volume. And if you are using the distance between the heater and the tray, then we use the meter rule to measure the distance between the heater and the tray. Okay, so you can't do it without meter rule. So the experiment you are planning, it must be such that you will use the apparatus given to you. Okay, you must use the apparatus given to you. You get it? Yeah. Okay, that's it. That is very important. So let's go. So I'm going to type it. Okay, I'm going to type the procedure. Let me pause the video so that it won't be too long. So that's the about the explanation. Okay, explain briefly how you will do the investigation. So I put it into writing. Okay, so I'll pour some water up to a depth of 1 centimeter into a shallow dish. Then I'll switch on an infrared heater and a timer at the same time and record the time taken for all the water to evaporate. And that's what I'm going to do. So when I switch on the heater and then I'll switch on my timer, I have a timer here. So and then I'll check the time taken for the water to evaporate. Okay. So after that, I'll record the time displayed on the timer. I'll record the time taken on the table. So I have a table of the depth of water and the time taken for water to evaporate. That's all. So I'll record the depth and the time taken. Then I'll repeat the experiment using other depths of water, such as 2 centimeters. So I'll increase the depth of water to 2 centimeters, and then I record the time taken for water to evaporate again. And then I repeat the experiment again with depth of water 3 centimeters, and then I record the time taken. And I repeat the experiment again with depth of water being 4 centimeters. So I'll just repeat the experiment, taking note of the depth of water and the time taken in both cases, and I'll record that on the table. That's all. Okay, in the shallow dish, and record the time taken in all cases. That's all. Then state the key variables that you would keep constant. So what are the variables you will keep constant? You put that into writing. During the experiment, I will ensure I keep the following variables constant: the distance between the infrared heater and the shallow dish. So in this case, I'm investigating the relationship between the depth of water and the time taken for the water to evaporate. So if that's what I'm investigating, this distance must be kept constant, okay? Because if the distance changes, I'm changing the rate of heating, and the rate of heating determines the temperature. Do not forget, temperature affects the rate of evaporation. So if temperature should change, then the experiment is not, the result you'll be getting will not be a valid result. So temperature must be constant. Hence, the distance between the heater and the water must be constant. That is clear, right? Good. Another thing that is constant is surface area. Okay, if some of the water is covered, if some surface is covered, then the rate of evaporation will reduce. So you want to make surface area constant. Also, wind. If you have wind blowing off the surface of water, then evaporation will be faster. So we don't want wind. Okay, so I ensure I keep the following variables constant: the distance between the infrared heater and the shallow dish, okay, just to ensure the temperature is constant. Then the surface area of the water, I will make sure is constant. Then the ventilation rate in the room by switching off the fan and the air conditioner. So the ventilation will be constant, by switching off the fan to ensure there is no wind throughout the experiment. So that's all. Those are the variables that will keep constant. Then draw a table or tables with column headings to show how you would display your readings. So you are not to enter any value. So the table, yeah, here is the table. You put the column headings, that's depth of water in centimeters, time in second. The table heading must also carry the SI unit. That is done clearly. Explain how you would use your readings to reach a conclusion. Okay, normally in a physics experiment, you would consider the trend of the values. You would consider the trends on the values you have. Another thing you can do in a physics experiment is to do what? Is to plot a graph of the two variables you are putting into consideration. When you plot a graph, then you'll be able to see clearly how the um, you'll be able to see clearly how one variable depends on the other. Okay, yeah, you're able to see clearly how one variable depends on the other. So in this case, you will plot a graph of you put time is what you are looking for. Okay, time is you want to check how depth affects time. So time is the dependent variable while depth is the independent variable. Okay, so you just plot a value of you plot a graph of depth of water in the tray against time taken for water to evaporate. So the time taken is what? The time taken is the dependent variable. Okay, while the depth of water is the independent variable. So you plot a graph like this. Time is what you want to see how it affects time. So time is the dependent variable, while depth is the independent variable. So you should be plotting a graph of time against depth because time is the dependent variable. Time depends on depth. So I'll plot a graph of time taken for all the water to evaporate time taken for all the water to evaporate against evaporate. So a graph of time taken against what? Against the depth of water in the tray. And then I'll calculate the slope of the graph. So when you plot the graph already shows you how the values scatter. Okay, it already shows you the trend. The graph already shows you the trend. Okay, so you can just proceed to draw the regression line and then draw a big right angle triangle and calculate the slope. So that is what you do for almost every physics experiment. Okay, it's very important you understand this pattern. Once you take this video from beginning to end and you understand everything I've taught here, it makes it easier for you to take other past questions on paper 6. Okay, so just follow this pattern. Okay, let me erase all the things you do not need. So just follow this pattern and your work will be perfectly done. Thank you for joining us today. Ensure you prepare very well for your upcoming exams. Download this past question paper and try solving it again. Okay, so don't just watch this video. Practice, download the past paper. Okay, the link to this question paper will be included in the description of the video. So ensure you download the paper and practice with it. Thank you for today. Ensure you come back to watch other videos so that you can make excellent grades in your exam. Do have a nice day. Goodbye.